Hi everybody. Let's go ahead and call this lesson I1, I for IB, and 1 for our first video. But truly, this is the beginning of section 4.5. And what we're going to study here are indeterminate forms and L'Hopital's rule. And so the beginning of this unit deals once again with limits, because there are some limits that we never really talked about. Let's say you're working through a problem and using all of your limit properties, and you find that the limit of whatever function that you're dealing with, maybe as x goes to infinity, ends up being 0 over 0. And we've always known that you can divide 0 by anything. You can never divide by 0, but 0 over 0 is what we would call an indeterminate form. And there's a reason that we call it indeterminate. So I'm going to write this down. Now, indeterminate so one value that a limit could take that would be indeterminate would be 0 over 0. And the reason that it's indeterminate is this. This would necessarily have come from some sort of function where the top of the function, maybe as x goes to infinity, approaches 0, and then the bottom of the function does the same thing. And so a lot of people want to say that's 1, but it could be 1. But what we have to think about is how quickly is the top approaching 0 relative to how quickly the bottom is approaching 0. For instance, if the top gets close to 0 very, very quickly, and the bottom part of the function approaches 0 very, very slowly, the bottom of the function will end up being bigger than the top. And in that case, this would end up equaling 0. But what if the bottom is approaching 0 very quickly and the top very slowly? Then you have some number divided by 0, and then the limit would be infinite. But you can have any value in between. And so we'll learn to work with these. We'll see how it plays out, and hopefully what I just said makes sense. Okay, another indeterminate form, say we're working a limit problem, and we discover that our fraction, the function that we're trying to evaluate, ended up going to infinity over infinity. Well, once again, you have to try to evaluate which part of this approaches infinity more quickly, the top or the bottom. If the top is approaching quickly, well, maybe the limit's infinite. If the bottom is approaching infinity quickly, maybe this value is 0. But once again, it could be anywhere in between, and it doesn't matter if it's positive or negative infinity over positive or negative infinity. Okay, so these are what we're going to call our two good indeterminate forms. We can work with them, but there are some other values that are indeterminate. And what we mean by indeterminate is you can't determine their value at a glance. You have to understand where these numbers came from. Okay, so another indeterminate form, infinity times 0. Doesn't make sense to multiply by infinity. So we're once again talking about a limit problem. Okay, so we have something here approaching infinity while another part of the function is approaching 0. We'd have to understand which is approaching more quickly. But this isn't a very workable form, and you'll see why. But we have methods to make something that ends up looking like this look more like these. Okay, another indeterminate form, infinity minus infinity. Okay, let's say we have part of the function approaching infinity, another part approaching infinity, and those values are subtracted. Well, you can't just say I walk out a number line forever, and then once I get there, I walk back the same distance. Okay, what we're looking at here is a comparison of rates. Okay, maybe this part approaches infinity very quickly, while this part of the function might approach infinity very slowly. And so you have this huge number minus a smaller number, and in the end, that would end up being infinite. Could be 0, could be negative infinity, could be anything in between. Okay, once again, we don't like this indeterminate form, but you'll see how we deal with it. Okay, another value that would be indeterminate would be 0 to the 0 power. Okay. Once again, I think this is the last time I'll say this, but you'd want to know how quickly is this part of the function approaching 0 and how quickly is that approaching 0. Another indeterminate form is 1 to the infinity power. Okay, and this one seems to confound students. They think 1 to any value would have to be 1. You could multiply 1 times 1 times 1 a billion times, and that would be 1. But remember, these are going to come from limits. We have something, maybe this something here is approaching 1, but it's always a little bit bigger than 1. Okay, maybe this something is approaching infinity, but maybe kind of slowly. Okay, and so you'll see that the teacher can make this equal any value. It just depends on what the beginning of the problem is. Okay, and the last one we'll talk about, infinity to the 0 power. Once again, an indeterminate form. Okay, and so a mathematician named L'Hopital came up with this very simple idea. And this is typically a student's favorite method for evaluating limits when they're difficult. Okay, so if I have the limit as x approaches a of some function divided by another function. Okay, and so you can see that we're dealing with a fraction. Okay, maybe it's a rational function or something like that. If this limit is either 0 over 0 or infinity over infinity, then the limit as x approaches a of the derivative of the top divided by the derivative of the bottom is equivalent to the limit that we started with. And I want you to think about what that means, but before you do that, remember when I was describing why these are indeterminate, these are rates. Okay, we're comparing the limit of the rates. Maybe we have a quickly growing function and a slowly growing function. Okay, so one very common mistake with L'Hopital's is to say, okay, I have the limit of a fraction, I have to derive, and students will want to apply the quotient rule. Note that this is definitely not the quotient rule. We're ignoring the bottom and taking the derivative of the top, and then separately we ignore the top and we take the derivative of the bottom. Okay, so let's go ahead and see our first problem with L'Hopital's. Problem 1. Let's evaluate this limit. That is not the word evaluate. All right, so problem 1a, we're starting off with a relatively simple one. Clearly we have a fraction of some sort, not a rational function, but still a fraction, and we want to evaluate its limit as x goes to 0. And like any good calculus students, your first instinct will be, well, let's see if we substitute the 0, and maybe that's all we have to do. And so 3 times 0 is 0, the sine of 0 is 0, and we get 0 divided by 0. So clearly one of our good indeterminate forms. At this step, I like to show the teacher that I have discovered that I can apply L'Hopital's rule because the hypothesis fits. And so I'll write LH with a little circle around it. And then what I do is I look at the top and I take its derivative. I ignore the bottom. So this limit is going to be equivalent to the derivative of the top, which is 3 minus cosine x, and then separately the derivative of the bottom with respect to x, which is just 1. And now I'll see if I can apply my limit. So I have 3 minus the cosine of 0 divided by 1. Cosine of 0 is 1. And so in this case, it looks to some students like 0 divided by 0 equals 2. But really what's going on is this top function is, as we get close to 0, the values are twice as big as the bottom function. Let's try another one. All right, so the first thing we really should do is see if we can just substitute the 0 in again. So I have the square root of 1 minus 1. And you want to definitely do this so you're indicating I have discovered that I have one of the good indeterminate forms. And that's what allows me to apply L'Hopital's. And so I ignore the bottom, I take the derivative of the top. And so think of this as 1 plus x to the 1/2 power. So it's a power function. The chain would be just a times 1, so I'm not going to write that. The derivative of a constant is 0. The derivative of x then, so I ignore the top now, is just 1. And so this is equivalent to the limit as x goes to 0 of 1 over 2 square root of 1 plus x. And now once again, after I apply L'Hopital's, I'll see if I can just substitute the 0 and then evaluate the limit. And I get 1/2. So now, here we had 0 over 0 approaching 2. Here we have it approaching its reciprocal. Now let's just do one more today. Make this 1c. All right, so we can't just jump right in and say, oh, look, we have a fraction, so let's apply L'Hopital's. We have to show that we can because the hypothesis fits. We get one of the two good indeterminate forms. And so I'll go ahead and try replacing the x's with 0 and evaluating this. Let's say I get 1 minus 1 minus 0 over 0, which is good. That's what we were looking for. And so I will apply L'Hopital's. I'll take the derivative of the top here. We just did this one. So this is 1/2, 1 plus x to the negative 1/2. That's 0. The derivative with respect to x of that is 1/2. And now ignore the top. The derivative of the bottom is 2x. I should probably clean this up. So this is the limit as x approaches 0. And then up top here, I have 1 over 2 square root of 1 plus x minus 1/2 all over 2x. And then I want to clean it up some more. So I'm going to express this as a single fraction. I'll have to multiply this by the square root of 1 plus x over itself. And so my numerator up top, can't forget my limit each time, will be 1 minus the square root of 1 plus x. And there's my common denominator. And then it's all divided by 2x, but instead I'll multiply by the reciprocal of that. And so up top I have 1 minus square root of 1 plus x. On the bottom I get 4x times the square root of 1 plus x. And now I'll try once again. Let's see if I can replace the x's with 0. So I get 1 minus 1, and on the bottom I get 0, so I'm kind of stuck here. I once again have an indeterminate form, but since it's once again a good one, the derivative of, let me see where I simplified things, where I first found the derivative here L'Hopital's tells us that this limit will be equivalent to this one. And then I know if I apply L'Hopital's to this, it's the derivative of the top and the bottom would be equivalent to this limit, and so by transitivity, equivalent to the first. In other words, we can just do L'Hopital's again. So I want to find the simplest form that I had and apply L'Hopital's to this step right here. So once again, I'll start it again right here. This is then equivalent to the limit as x goes to 0, the derivative of the top, so I have 0 and then minus that again. The derivative of the bottom, so this is a product rule now. So I have the first times the derivative of the second, and then plus the second times the derivative of the first. I'll write that like this. Okay, this is getting ugly, isn't it? So maybe what I should do then is just see if I can substitute the 0 in at this step. And so I have -1/2, 1 plus 0 to the -1/2. This is nice now because that's simply 1 on the bottom. Looks like I have a 0 on the bottom, but that's just for this term. Note that I have the second term. So, I can replace all of this right here. All the x's with a 0, but I know that that term will end up being 0. So then this last term here and maybe I should have written that as square root, but simply 1 again. So I get -1/2 times 1 divided by 0 plus 4, which is -1/8. Okay, and so we'll go deeper into this lesson tomorrow. Eventually, when we finish section 4.5, you should be able to do 1 through 10 on the review. You can glance at them, but there are so many little twists that we haven't talked about with L'Hopital's. Good luck.